There you go. Awesome. You're in charge.
The meeting is being recorded. Got it?
Oh, can you give her screen sharing, Paul?
Yeah, because so far it doesn't work yet.
I get Goon Squad points here.
Yeah. Okay. Now I can go back to. And now it. Ah, okay. Ooh, this is the first time it actually has it right. That I get the presenter view here.
Excellent. All right. Welcome to this pre-EGU ESRG seminar series for our lunchtime series. This week, I have the great pleasure of presenting Kerstein Lehnert of Lamont Doherty Observatory at Columbia University. She's going to be talking about fair and open data, which is how I originally became aware of her several years ago at a meeting related to the Deep Carbon Observatory, where she introduced to me one of my favorite data concepts, gray data, which is all those lab books and hard drives that you have laying around but have never been published. So she's going to talk about a lot of her efforts there and hopefully touching on some of her one of our areas that we're collaborating on, which is on looking at archiving and curating Astro Materials data. So with that, I will let her go. And yes.
Yeah, okay. Well, thank you for having me here. It's great. I was here in August for the Meteorological Society meeting, and I loved it in Glasgow. So it was a pleasure to accept the invitation again to come here. And I hope to hit some nice pubs tonight again. Okay, I hope that this will give you a bit of an introduction to all these issues around data that we're having right now. And just to start off, I wanted to warn you that I'm a geochemist, and the data I'm working with in our data facilities are sample-based data, lots of geoanalytical measurements that we're dealing. So it's a bit of a biased view of when, what data management is about. But I'm sure that all of you are aware that data has become like a big topic, both in government and society, but for the sciences as well, and that we're seeing this explosion of data volumes that are being generated. And I'm not talking about all the cell phones and stuff that's happening, but for science as well. And that creates a lot of challenges, but it also creates a lot of opportunities for science. And we see that increasingly. These are just a few examples of, where communities in the sciences and in society have basically taken this vision of harnessing the data revolution. It's you can read it for yourself, basically, anything from food and water to the Sustainable Development Goals. And it's always this term of harnessing the data revolution. And that is happening in the earth sciences as well.
Can we pause a second?
Sure.
They're recording your screen here, not this lovely screen.
Oh, wonderful.
So, which is,
well,
it's fine, but we'll do that. And no. And
generally, I'm taking this as a moment. Oh, you're already doing it. I still want to take that moment, trying to understand the audience that I'm talking to. So who of you is generating data? Okay, wonderful. And are you also using data from others in your research? Okay. Because that obviously always matters. This is a graph. I just got a renewed version from Brooks Henson of AGU. He's the science director there, showing how the use of machine learning has exploded in the earth sciences as well. These are the numbers of abstracts in the AGU fall meeting that mention machine learning. And so you can see how this has rapidly grown up. It always was, not always, but it clearly, application of machine learning, data analytics, modeling, and so on, has been big in what we call here the big data. And in the earth sciences, you have big data coming from satellites, coming through large observation networks and so on. And these have always been quite well organized. They are so big that nobody else, nobody stores it on their local computer and so on. But then we have this long tail of smaller data. We have often referred to it as long tail or small data. And those are data being generated by communities that usually work on samples, just small data that are created because of the intensity of actually creating this data in the lab. But now we're actually seeing the demand for data science in these fields as well. And I kind of compare this often to creating a puzzle from many small pieces. What we need to do in these sciences is take all the different data sets that are being created and put them together so that we can see the larger patterns, be they in space, be they in time, be they with respect to properties and so on. So that's our destination on this, from data mining to data mining. We want to be able to dive into the data and take the most out of it. And we have fortunately seen some of, we have some examples where we can show how the data management that has created large data sets, consistent data sets that can be accessed through machines, through computers directly, can lead to new science. And this is an example where Brennan Keller and Blair Cheney have used our data systems in geochemistry to really analyze large numbers of chemical measurements, and that way actually came up with something called statistical geochemistry, which didn't exist before. Large volumes of data could be accessed and mined. And this is expanding into other fields. This is a graph from Anirudh Prabhu and Shauna Morrison at the Carnegie Institution, now building a vision for mineral informatics and what you can do if you have the data resources from all these different data sources on the right side. And I'm sure you can't read really all these science questions that they put out. But what it shows, and I like this graph because it shows that certain questions require all these different data types that you need to link to and bring those together. And again, that doesn't work if we have data that are not accessible, that are not reusable. This is another example, actually machine learning now in paleoecology, another field that doesn't have usually the big data sets. In all of these cases, what you need is a data infrastructure that makes this data available in a consistent manner and with really structures that can be machine readable. So when I thought about this from data mining, it's to data mining, we have to address a lot of cultural issues, technical issues, and policy issues. And I think on the way to get from them just holding on to your data and working with it yourself, while not sharing so that we can build these large data resources, we have to come first of all to the step of, sharing our data in an open way. Then we need to make these data fair, and FAIR is an acronym that stands for findable, accessible, interoperable, and reusable. And I will get to that a little later. The highest level sort of reusability is analysis-ready data. And it's a term that's usually used for remote sensing data, but I think it's very applicable to any data. If the data is in a state where you can actually perform analysis and not have weeks of wrangling data into a consistent structure. So first of all, we want to make data open. And there is a huge movement worldwide to actually get that done. And this is a report from the National Academies in the US that has basically created the vision of openness, of sharing information, and other products of scientific research, which includes software, which includes samples, which includes workflows, and so on. But there are lots of reports, if you go online, that have been generated by other governments. I've tried to find things for the UK. There isn't that much, which surprised me. But I'm sure there are instructions from the funding agencies here in the US as well. So most of the funding agencies and government agencies in the US have just declared 2023 the year of open science. Specifically, NASA has created a whole new program for transform to open science. So there is a large push to actually make this open data world happen. So just to give a definition, what does it actually mean, open data? I mean, obviously everybody can think of something that's accessible, but it really needs to be clear to everybody what you can do with the data. There needs to be a license with it. It must be accessible. It doesn't mean it's free. There can be a cost attached to data access. And the interesting part is, I think, it needs to be compiled in a way that makes it machine readable, that you can actually digitally access the data without having to transcribe it, which means, a lot of the data in publications, you may know, is still in PDFs or in even tables that are in JPEG or in other sort of image formats rather than in a machine readable way. And they need to be shared in a non-proprietary format. And we were just talking about it, that there's still manufacturers that have not caught up with this requirement. But the question is, if data fulfills all these requirements, is it really ready to be mined and analyzed? And it clearly isn't, because you can put it out with a license on a website, but that does not give us the data resources that we can really use. So because in many ways there are cultural issues related to the sharing and integration and access of data. And that is, this first point here, open data have to have identifiers. They need to be really explicitly identified and entered into the public record, so people can cite these data and can find and access the data. Obviously, they need to be accessible, that's clear, so they can be opened, read, and processed. But the really important part is that they need to be documented in a way that anybody who wants to reuse them can make sense of the data. And that is the big issue for many data types out there. What is that information that you need to capture? So these requirements have kind of led to something called the FAIR principles. I explained that already. Fair data are accessible and understandable, both for humans and machines. This is really important. The FAIR principles were really in the first place created about machine readable data. They need to be deposited in curated, certified, trusted repositories. Your website doesn't do. That's, it needs to be a repository that follows international repository standards. And then the data need to be citable. It means that they are registered in a system that gives them persistent identifiers such as DOIs, which you're probably all familiar with, and should have clear usage licenses. And then again, they need to be documented by rich metadata that support discovery and reuse. And that's why I wanted to briefly talk a little bit about metadata. So metadata is essential information about the data that helps to both find the data, search, providing search criteria, and they allow to understand the data. Without certain information, you simply can't do anything. I'm trying to think of an example. I think, for example, if you don't know the method with which the data have been generated, or you don't know if data have been normalized to certain standards and so on, you can't compare data if you don't know that. And in order to be useful, and specifically with respect to discovery and the reuse, metadata should be standardized. And this is a big issue because even if people provide metadata when they submit their data to a repository, it is often not following any standards. And the problem being that these standards actually don't exist for many domains that we have. And yeah, metadata can be generated automatically, harvested, read out of the digital data already, but that's usually very basic information. So there's manual curation, which is costly and a burden to people. So with respect to the standards that I mentioned, standards mean that there are vocabularies that everybody uses in the same way, because if you name a rock in 5 different terms, but all mean the same, it's becoming really difficult to integrate data, to find data, and so on. The data needs to follow a certain structure, a metadata schema. There are general concepts such as dates, names, and places that are obviously more standardized, but the issue is discipline-specific schemas. And so in all these different fields, in the earth sciences and biological sciences, everybody has to come to an agreement, basically. What do you need to understand the data? And that can be very different. In the earth sciences, mostly it's geospatial information. It is information about the methodologies, about the manipulation of data, and so on. So we dealing often in the geochemistry with a huge number of data types, and just walking through the labs here, you have a lot of different machines, and the different machines all need to in some way be documented in a different way. Some examples that I can give is in the biological community. Darwin Core is a standard that's used for describing biodiversity specimens. In the planetary science, the planetary data system metadata kernel 4 is being used. Seismology has a standard, but many other communities don't. And then I already mentioned DOIs as the persistent identifiers. And I specifically wanted to show this slide because it is a really important concept to have persistent identifiers. It ensures that you can always find something. You can always locate a digital object. If you would link to an object, just giving the address on the web, you will at some point, sooner or later, get a 404 error and not go anywhere. The persistent identifier ensures in some way that that location is always available because it goes through a set of metadata. And so examples for persistent identifiers include DOIs for data, for publications, ORCIDs. How many of you have an ORCID? Everybody? Ah, fantastic. IGSN. Who has heard of IGSN? There we go. That I should have made all my talk about IGSN. IGSN is a persistent identifier for physical samples. So if you collect physical samples and you really want to make sure that you have a persistent connection between your data or your publication and the sample, and you can track your sample through its lifetime in the labs and in the archive, then you need that persistent identifier. In the meantime, RORs are identifiers for research organizations. The reason why these identifiers are so critical is that you can properly cite objects. And citation of data is important for the adoption of these new concepts of open sharing and fair data access. So being able to cite is important for the data users because they can provide evidence that enables reproducibility of the research for others to use. It obviously increases transparency again because everything can be accessed, and it encourages reuse of the data for new research questions. For the data providers, the ones who actually make the data available, have created the data and make them available, it's important to get credit for the data. If data are cited, you can actually get something out of it. It makes your data more findable, and it allows data repositories also and publishers to track and measure the impact of the data. We, from the repositories that I operate, we send out regular notices to the users saying your data has been cited that many times and so on. You can only do that if you really use identifiers. And I just wanted to add this, that by now we have had citation of data for some time, even though it's still not in its optimal state, but it has happened. And studies are now coming out that show that those papers that make the data publicly available in repositories have a higher citation rate than the papers that keep the data just in the paper. So again, important to me to mention community standards. And that to me is that step from fair to making data analysis ready, because the standards ensure that there is consistency, that data can be integrated, they can be searched and evaluated in a consistent manner. So what that means is that disciplinary communities actually have to come together and work on something like this. And this is often not easy because there's so much fragmentation in, communities work nationally, they work in certain scientific programs, they all have their own ways of doing things. And so if you want to create a global standard for a certain domain, you run into a lot of challenges. So what these standards really need to do is say, what is the information that we need to capture from the beginning of any measurement on, so that it can be reported later with the data. We need to agree what is the terminology, what's the language we want to use. And so, coming back to the challenges that I mentioned, it's very often the question, who is actually the community? How do you define who has a say in building these standards? who develops and governs them in the end? You know, if changes have to be made, if, you know, somebody says that's not a term that I can use, who makes the decision to take that term off? And then something we also talked earlier about already is when it comes to defining these metadata standards, there are always people who want to get everything, any information about the data you create. And then it becomes a huge burden in putting all that together. So how do we keep the balance between getting what we really need to reuse the data and not overburdening each researcher to submit that information? So sometimes you don't get anything if you ask for too much. I need actually to take it. So I see, you know, what I wanted to talk about with respect very specifically to the geosciences and the geoanalytical data are 3 points or 3 steps. Look at what the data culture is right now. Look at some data services that my group provides for open and fair geoanalytical data. And then what we do to achieve analysis-ready data. So our starting point is something like this saying, you know, do you expect me to give away my data? People still say that a lot, especially in the geoanalytical community. I mean, historically, geochemical data has never been very accessible, and it has been sporadic and, yeah, bits and pieces all over the place. I love the thumb drive symbol that my colleague Leslie Wyburn from Australia has been using. She says the geochemists don't share data because they don't have to. It all fits on a thumb drive. Those communities that had the big data, they had to come up with data centers where everybody shared the data. Geochemists don't do that. Now that's changing, you know, and especially when we're talking now about the future of geochemistry, there is a lot of data being generated through imagery, what we're working together on. But historically, that didn't really happen. It was data tables that people shared. So the norm in geochemistry is very often still my data, and I'm not going to share them except through a publication. Another challenge is that, you know, besides the Earthchem database, and there's another database in Germany, GeoRock, there aren't that many repositories for geochemical data. So there is a gap in the infrastructure, and all these data systems are not well supported and always at the risk of dying because there is no sustained funding. But we've started to really recognize, I think the community, not me, but the community itself has started to recognize that we have to change the way we do our research. And I'm very glad to say that that's really coming out of the early career scientist community. So last year we had a session, a great debate at the EGU meeting that was called here, where is my data, where did it come from, and how was it obtained, improving in access to geoanalytical research data. And we also ran a webinar about that. It was a panel of more senior and more junior people who talked about their desires as a scientist, as a geochemist, to access data and where they saw challenges and so on. And so I've just copied one of the slides that Steve Goldstein gave in the panel about should scientific data be public and fair. And it's really a good set of feelings that people have now in, you know, data are the foundation of our ideas. We need to be able to evaluate those ideas, and that's why we need access to the data. Good data is long-lasting. It can be reused over time and inform new science. And, you know, this to me is always one of the most important arguments is public funds were used to generate the data. So they don't belong to you, they belong to the public, and everybody should be able to take advantage of the data. So the question is not whether scientific data should be public and accessible, but rather how to make it so. And that is obviously quite a challenge to achieve. So first of all, as I said already, cultural barriers exist. Many are afraid if they put their data out, somebody else will take it and work with the data before they themselves can do it, and they feel scooped. Until we really have data citation fully implemented in the community, there is a lack of getting credit for the data. So, you know, policies and procedures for data citation, again, really important. The burden for researchers is clearly one of the big obstacles. So we need easy ways to share data. We need support for that and funding for it. Again, there's lack of sustainable infrastructure and lack of community standards. But we do have domain repositories, and they also need to operate following certain standards. And I'm going to get a little faster because otherwise I'm going to be running out of time. And so I'm coming to these, this is very dark, but to the data services that I'm operating and how we have tried to make data open and fair in the geochemistry, petrology world, and anything that has to do with samples. So the three systems that we operate is Earthchem. Has anybody used Earthchem? Oh, cool. Earthchem is a data system primarily focused on high temperature geochemistry, but the repository is actually more used by low temperature geochemistry environmental data now. CSAR is the system for Earth sample registration, and it basically supports what I mentioned earlier, the unique identification of samples and the cataloging of metadata for samples so that people can find out what samples exist and can see if they're using these identifiers, what the information about a given sample is that's out there. And then the third system is the Astro Materials data system, which is a system for Astro Materials samples data. This is a great team that I have with me. It's a mix of data curators and software engineers. As many of the data facilities, it's a difficult process to mix the two groups, those who have the disciplinary knowledge and those who have the computer science and software engineering knowledge. But I think that's the unique feature of this group, that they work really closely together. We also have cloud experts and digital archivists and so on. So you can see what the range of talent is that's needed to run a repository. We have set ourselves goals that are not only to make the data available, but to also change the culture. So a lot of what I mentioned earlier with respect to the challenges of creating fair and open data is to educate, to train, to help and engage researchers in doing better data management. So what these systems provide is basically services for the publication and preservation of data, but also for data mining and analysis. And then, as I said, CSAR is sample discovery and management. And these two other, the best practices and standards, really focusing on improving the overall infrastructure. And the way the systems work is the repository is a place where users submit the data and the metadata for their samples using templates. The data goes into a file system, and on top of that is the metadata catalog that can be searched. So this is really focusing the repository on findability and accessibility of the data. For interoperability and reusability, we actually take whatever data is appropriate and stick them into a relational system where they get harmonized and become really a consistent large data set that can be mined, visualized, analyzed in whichever way. So Earthchem and CSAR are part of a project called Aida II that's funded by the National Science Foundation, and it's a collaboration with multiple organizations. And we see these systems increasingly as building blocks of a more integrated structure of data for samples that all interact with each other through things like the persistent identifiers. So Earthchem is for geochemistry and CSAR for the samples. And we have a third system called the Library of Experimental Phase Relations that holds trace element and major element phase equilibria and trace element distributions. This is a newer project, and I will just briefly talk about it, what's happening with the Astro Materials data system. We have been working for a number of years now to build this system for NASA. It holds at the moment data for all the samples, not yet for all, we're still working on it, for samples that are curated at the Johnson Space Center in Houston by NASA. But we're now asked to get the system ready to archive all the data from samples that will be collected in the future through sample return missions. You might have heard about Artemis and the Mars missions. Right now, we're getting ready to accommodate the data from the OSIRIS-REx mission. And the new thing that we're working on, and where I'm so glad about the collaboration with Josh, is that here we're moving from our spreadsheets with geochemical compositional data into a world of imagery, of two-dimensional, three-dimensional imagery, which is really new for us to build an archive that needs to accommodate this volume and actually also diversity of the type of images that are going to come. So we're really at the moment in a big development phase there. But we want to build the system in a way that it kind of mirrors what Earthchem has done. And so we have created a synthesis similar to what Earthchem had to provide, a way for advanced analysis, which is something that in that community has not yet quite happening. I'm going to go over these. I wanted to emphasize that every data set that we get submitted by researchers goes through a curation workflow. And this is the way we really ensure quality of the metadata. So you cannot publish unless you have provided a certain basic set of metadata and meaningful metadata. So what our curators look at is really, what have you filled in? Is that something that makes sense or not? And this is obviously a process that slowly but surely we need to replace with more automated processes because it doesn't scale. But we still want to keep the actual eye on the data. This is just when you publish a data set, this is how you will see all the metadata, and you will have a link further down, I think, to actually download the data. The metadata links to things like funding awards, but it also links to all the samples. And I think this is really important for the future connection that we make between the data, the publications, and the samples. So you can find publications that have data for a given sample in an unambiguous way. We also make all the metadata machine readable, available for search engines. So through the Google data search, we'll find everything that sits in our repositories. And other more scientifically oriented search engines like Data1 also do find it. The interesting thing is the adoption of the systems. The synthesis has been around for a long time and has been used, but in the repository, we didn't get a lot of submissions. And the bump up here, as you can see, is around 2019, where way more data sets started coming in. And that was when publishers changed their policies that data needs to be open and submitted to a repository. So it's happening, but still not enough. So a big focus for our repositories now is to make it easier for researchers to submit their data. Currently, as I said, there are templates, and for each data set, you need to fill out a template with more or less, often repetitive information because you use the same method over and over again. So what we're trying to do is make the whole system more modular, that if you have sample metadata submitted to the registry and you have IGSNs for the samples, you only need to fill that out once. When you submit your data, you use the IGSNs and we can pull the metadata from that system into your data set. Same with method metadata. Right now, it all needs to be entered. What we're trying to do there is build something we call a method directory. So you enter information about your analytical process or how you process the raw data to actual data products. You enter that once, you can version it as things keep changing, but then you can link all these different data sets that you generate over time to your method description. That is like a small publication, has a DOI, and all you need to do is add the DOI to the metadata of your data. And then you can generate, your own method dashboard with all the methodologies that you have. So I talked a lot about community standards earlier. What we're also trying to do is get people to come together, get researchers who work on the same problems or who work with the same data types together and talk about what are their best practices and share those. So we have established a concept called Earthchem Communities. We basically give these communities a web page where best practices can be advertised, where people can communicate about any relevant developments. I think our most active one is the TEFRA community that has created best practices for sample documentation, best practices for field documentation, and mostly, I think, was Microprobe and ICP-MS, where they established their own guidelines in how data should be shared. So this is a way for us to slowly but surely bring people to talk about best practices. It's not ideal because it's obviously still too fragmented, but we can take what comes out of these different communities and kind of synthesize this. So last step, and I know I'm getting late, is the data mining, what we've done there. And as I said before, we've taken data and put them into these large-scale databases. So we have, oops, now I see that. The Earthchem Portal, which actually brings together data from different databases. I mentioned GeoRock as a database run in Germany, the US Geological Survey databases, and so on. We now make available 50 million analytical data points. So that is a real large data store for geochemistry that can be mined. With Astromat, we're now at 1.3 million data points, so it's growing fairly quickly. And all of these data systems really allow you to do data mining and statistical geochemistry. We're getting increasing requests for the whole database to be provided to somebody. And this is creating a lot of challenges for us now, in that our architectures basically don't accommodate these large requests. And we've been starting to create APIs so that people can use their Python notebooks and so on to access the data and then directly work with them. I'm going to go over that. This is just the still existing graphical search interface, obviously, where you can use criteria such as sample type, your geospatial coordinates, age, and so on, to actually find data across many publications and then get back a data set for that. I'm going to jump over that. Well, just to show you 3 quick examples where publications have recently come out that actually take advantage of these data, large data syntheses. This is a publication by Maurizio Petrelli, where he actually summarizes what type of petrological problems you can address through machine learning. And they have applied it to tectonic discrimination. Another approach for tectonic discrimination has been to look at trace elements in Zircon. That's another, I think this is still in preprint, this publication. But again, you can see they used rare earth elements from 13,000 data points. It's basically impossible to do something like this on your own going through the literature. It's just too much. Another interesting use case was that the database supported a response to a manuscript review, where a reviewer was questioning some of the conclusions in the paper, and the authors were able to go to the database and access this. And in this case, it was mental xenolist data, to access all the data and then come up with an answer to that reviewer's question. So there are different types of benefits in this. Now, tell me if I should stop, because I'm not sure. Yeah, that fits about. This is just the last step in the whole thing, is that even though, GeoRock and PetDB have created these large syntheses, the landscape remains fragmented. There are lots of other different databases that are being put together, and we can't connect them because they all look different. They all, again, are missing these standards to bring the data into an integratable format. So what we did a few years ago, several efforts came together and said, we need a standard, a real technical standard to exchange geoanalytical data. And so we founded this initiative that we named One Geochemistry, that is trying to develop these data standards for geochemistry through coordination and collaboration among these large data systems. And we have here in Europe, the Geoscience Research Center in Potsdam is part of it, but also the EPOS multi-scale laboratories. I'm not sure you are familiar with the European Plate Observing System. They have a whole component that has a network of geochemical laboratories in Europe in it. Obviously, yeah, I mentioned it's, creating best practices and standards for fair geochemical data, interoperability standards, but then also providing this governance that is so difficult to get. So I think this is my last slide, which again goes back to my colleague Leslie Wyburn, who integrated this statement by Benjamin Franklin that we must indeed all hang together, or almost surely we shall all hang separately because we can't achieve what we need to achieve with data. So we need to work together, and we need these standards. As painful as it is, it's a necessity. It's no longer an option. Okay, thank you.
All right, well, I have time for a couple of questions here. Do we have any from the audience?
Oh, it's a business model to store data in the cloud. Now, I appreciate a lot that some of my data are available, free, accessible, and so following the fair guidelines. It is still there. Someone is paying basically the bills to run the server. Are you afraid that you're running out of money at some point? Or where do you generate money? Because I don't put it in my grant application.
Yeah, no, I mean, that's the big question. And, a big point in this discussion last year in the great debate, who pays for this? The repositories are supposed as their standard to show what their sustainability model is. Now, many get funded through governments, but most of them are not, long-term. They get funding for 3 or 5 years, and there is a danger that, something happens to the data, what will. So, I mean, it's a real problem still. The institutional repositories are clearly sustained. But again, there we have the fragmentation, and nobody in the library who runs the data repository for a university cares about the geochemistry data standard or the data standard of seismology, so that it's not a solution. And there has to be really that dialogue with governments. If they want data to be publicly available that comes from science, then they also need to fund an infrastructure to support it.
Part is also maybe us as researchers, when we write a grant, you put in a certain amount of money that will contribute.
Yes, and I know that, I mean, in the US, the National Science Foundation would like to do it that way. But, they're talking about $200, $500. We get 400 data sets, right? That doesn't even pay for a couple of months of the staff, right? It's not a cheap enterprise, but you have to, on the other hand, see what would it take to recreate all the data, to recreate the samples, go back out there to Greenland or Antarctica, and that's basically the argument. And that's why I think NASA is putting real money into this, because they know they can't travel easily back to asteroid Bennu and pick up a few more samples. That whole mission costed $1.5 billion. So you can put 2 million into running a repository that sustains this stuff, right, in the long term. But that recognition is not yet there everywhere in the earth sciences. Yeah.
using the data either incorrectly, sometimes contextual information that can be control of slightly set. So if someone does have to do the data analysis, it's taken out of context, and then that data is misused. I think it's backing up.
Yeah, no, that's a big problem that, it's hard to overcome. I mean, it's the same with published research, it can be taken in different ways. And you don't even have a guarantee that somebody cites. You put a license on, you have a copyright, so to say. That's basically all you can do.
You're just hoping that the reviewers won't publish.
Yeah, I mean, that's review, if that gets reviewed, and if it's obvious that something is wrong there, that's one way to find out. But I mean, the experience with the review of data has really not been great. Reviewers don't look a lot at the data. That was another outcome of clear statement in this great debate that, in order for the data to be in good shape, we need the curators who are focused only on the data. So it's not solved yet. I mean, I think that the more information you have about the use of the data, you have the code that you use to do something, and people can reproduce results, then you might find out that something is not correct in the process. So that's another advantage of making sure there's reproducibility in the publication.
Yeah, so many of the potential new applications that you highlight are around, it's like machine learning, sort of interrogating big data sets. There's a heavy kind of secondary data version that's is quite intensive. Codes that are maybe doing like color analysis or some classic quantities of secondary information to interpret that primary data. Do you envisage a role with these sorts of platforms and documenting that process through storage and reproducible? It's a lot of that could also be applied to models.
Absolutely. I mean, there are communities that have repositories just for their models and the code. I mean, and we get more and more submissions that have code with it, and with it, what we're going to do, I mean, for now, we're telling people to put their code into GitHub, send us, a version, and register that. I mean, there are repositories such as Zenodo, it's a way to actually get a DOI for a GitHub repository, and then we link it to the actual numbers. But I think this will become much more of an issue that we need to make sure that code works. But, again, something we talked about earlier is that code is also difficult to archive because it evolves so fast. So you can put models by themselves, the output basically into an archive. And as I said, it's happening. It's for us, we will have to figure out. But then again, the whole funding doesn't scale up to doing all of that.
I think that's it. Do you have any questions online? All right, with that, I'd like to just thank our speaker one more time. And yeah, thank you.
Whoops.